All right, let's continue with lecture 7. So last time we talked about the concept of static equilibrium. So we said if a rigid object is not moving, it's just sitting at equilibrium, then it does not have a center of mass acceleration, therefore the net force acting on it is 0. Also, it does not have angular acceleration around any axis, therefore the torque acting on it must be 0. And we can write the torque around some arbitrary axis in this case. So if the net forces add up to 0, then we can just verify that the torque is 0 around one axis, and that implies that the torque will be 0 around any axis. So we did one problem and a couple of questions involving static equilibrium. So brief review of what we did last time. We just had these two main equations. In static equilibrium. So let's have a quick question just to refresh your mind about this, and then we'll switch gears and talk about a new topic. So the topic for today is rolling without slipping. So we will be talking about a particular case where we have a combination of translation of motion of the center of mass and rotation. And we talk about the geometric constraints on this and try to get more practice. All right, so here's a quick question. Slideshow. All right, so take a few minutes or a few seconds, maybe pause the video and think about the correct answer. All right, so what did you get? So we have, in this scenario, we have a massless rod, right? A weight of 1,000 newtons is hanging from one end. The other end is kind of pivoted. It's connected to some hinge, and in the middle there seems to be a scale, so it exerts a force and it can measure the force. So what would it read? Yeah, so what can we say? Well, if the rod is in equilibrium, we can think about the net torque on this rod. So we have some forces at the pivot point, the left-hand side of the rod. And if we don't want to mess with them, we just put our axis there, which is a natural choice here, and calculate the torque around that. So then the 1,000 Newton will give us 1,000 Newton times the length of the rod, and that's a clockwise torque. So it wants to rotate the rod downward. And then the scale is pushing up on the rod, and whatever its force is, it's going to multiply half of the length of the rod. So it's a force with an arm that's half the length of the arm for the 1,000 Newton weight. So in order for the torques to be the same, the force must be twice as large. And that gives us an answer that's 2,000 newtons. Okay, so now this is the new topic, the main discussion of today's lecture. So you have a lot of experience, of course, with rolling, but you may not have thought about it in much depth, right? So basically like the tire of a car, right? If it's moving as expected, if it's not like on some slippery, icy road, or if you haven't jammed on the brakes, if you're just driving along, the tires roll on the ground. The wheel of a bicycle does the same thing. You can try to experiment a little bit. Just take a coin and try to slowly roll it on the surface of a table. So definitely, like, its center of mass is moving forward as it rolls. and there is some rotation, right? So we want to try and make sense of this type of motion, which involves rolling of a round object on some surface, and there is no slipping. We talked a little bit before when we were talking ropes and pulleys, etc., about slipping. Slipping means no relative motion at the point of contact, right? So if I have a disk, for example, that's rolling on a flat surface, the bottom of this disk, which is touching the ground, should have instantaneously a velocity 0 because the ground is not moving, and instantaneously there's no relative motion between the point of contact and the ground. So instantaneously the lowest point of this disk must have a velocity 0. All right, so we're back here, so let's try to get more intuition about this. So we want to talk about rolling without slipping. So imagine that's our flat surface. This is a disk, a round disk. This is its center, which is also its center of mass. We assume the mass distribution is uniform or at least symmetric around the center of the circle. Now, this point instantaneously is not moving, right? So what happens? If you look very closely to this, if this point is not moving, how can this disk move forward? Well, instantaneously it can have a rotation around that point, right? So if you imagine this point is pivoted and you rotate a little bit around that point, so let me draw a much bigger figure like that. So that's the point. Then you rotate by some tiny angle around this. So now this point that's a little bit ahead comes down and touches the ground. And this original point, let's represent it by some triangle, will be here. It gets lifted up. Okay, so that's a really terrible figure. Let me just try to do better. Let me go here. So we're zooming in very closely around the point of contact here. Right, so that's the point of contact. Let me put a triangle to represent a point on the wheel. And this dashed line is the ground. So then the whole thing rotates around this point, and a little bit further, suppose there's another point on the wheel, at the edge of the disk or the wheel. And then a little bit later, all of these points kind of touch the ground, and eventually we'll have this point here touching the ground. And we can look at the length of that curve, so our original point will be here. So one way to view this type of motion is that instantaneously, if you look at very, very tiny time scales, it looks like you're rotating around the bottom point that's touching the ground. Yeah. So if an object is just rotating, the point that's not moving, that's stationary, is the point around which you rotate. However, the actual point on the disk where you rotate around, which you rotate around, kind of changes as you roll, because then that point after a little bit lifts up from the ground, and then the next point will be touching the ground. So in the limit of tiny changes and tiny time scales, we can view this entire motion as instantaneous rotation around the ground. So So let's see how we can make sense of this. So if that's the case instantaneously in the limit of really tiny time scales, if that's the instantaneous pivot, then we can get all the velocities from this. Because again, this is a rigid object, right? So there is going to be one angular velocity associated with this entire rigid object. So then, you know, if you want to get, for example, the velocity of this point here, center of mass, well, if that length is r, it will be like this. It's tangent to a circle whose center is that instantaneous pivot, and the velocity we know for rotation around the circle is v equal r omega. If you want to look at this point here, it's all the way over here. So now it's again tangent to a different circle, if you wish, and now the distance is 2r, so the velocity of that point will be 2r omega. If you take some arbitrary point, so let's say I take some point over here, it does not even have to be on the edge, so let's make it even more arbitrary. Take some point here on the disk. What is its instantaneous velocity in terms of omega? Well, first, I mean, if I think about an instantaneous rotation around that point of contact, well, instantaneously it looks like it's tangent to a circle like this. So if this distance from here to here is L, from the bottom lowest point to the point I'm interested in, and then its velocity is going to be tangent to that circle, perpendicular to this line I drew from the point of contact to the point I'm interested in. And then I just have to multiply L, the effective radius, by omega. So this is one way to visualize rolling without slipping. It's just working in the reference frame that's attached to the ground, in which the ground is stationary, and instantaneously the velocity of the point of contact is 0 because it's not slipping with respect to the ground. So for very short times, we can view the motion as rotation around that point of contact. All right, now there is an alternative way to view this motion. So suppose you move with the center of mass. So suppose you have this wheel that's rolling on some flat surface, and imagine this wheel is really huge, so you can maybe put a chair here near the center of mass and you just sit there with your laptop, and then the disk is rolling, so you're there. So basically this chair will be moving this way, right? As the disk rolls, of course, it's going to be somewhere on the surface. If you forget about its rotational motion for now, the center will be the same distance from the Earth, the radius, so it will be just moving along a straight line parallel to the ground. So if you're sitting there, what are you going to see? Well, the only thing you can see is that you see the center is stationary, is fixed, it's not moving, and then the only thing that can happen is that the wheel can be rotating around its center. So from the point of view of an observer that's moving with the center of the disk, the only thing the disk is doing is just rotating around its center, right? So that's the idea of relative motion and different reference frames. So you may have seen this in 161, but it may be worth reviewing. So suppose you have one reference frame, let's say x and y, and you can represent the position of some point by some vector r, which is x times the unit vector I here, plus y, the unit vector j. Now consider another coordinate system, x prime and y prime, whose origin is at some vector, let's say r, which has again rxi plus ryj. And then the same point will have will be represented in this other coordinate system by a vector, let's say r prime, which is x prime I plus y prime j. Okay, so so definitely, like, let's call this the vector r. So the vector r here, this vector, you can see visually that it's the sum of the vector r, the position of the origin of this primed coordinate system, plus r prime, the position of the point I'm interested in this new coordinate system. So that may be a little bit too much information, so you can just, for the sake of the argument, just to give you a simpler version, you can think about maybe this is a one-dimensional case. So one point has a coordinate x in a given one-dimensional coordinate system, and then we have another coordinate system. So let's say its origin is here, a distance r away, distance rx away from the origin here. And then if the coordinate of this point in this new coordinate system is x prime, I can write x is rx plus x prime, right? It doesn't say anything more than that. So now if you take the derivative with respect to time, you find the velocity in original, in let's say xy frame, is dr dt, velocity of the moving frame, of a moving frame, plus v prime, the rate of change of r prime with respect to time, which is velocity in the moving frame, right? So as an example, consider a train that's moving with some velocity, capital V, and then someone inside the train throws a ball, and that ball, to the point of view of this passenger, is moving with some velocity v prime, which means relative to the walls and floor of the train. So from the point of view of someone sitting here outside, the ball has a velocity, let's call this let me call that u, just so we don't confuse. So the train is moving with velocity, let's say u. To this external observer, velocity of the ball is v prime, is v, which is v prime plus u, right? The train has moved forward by some amount, and the ball has moved forwards even more than the back of the train. So these things add up. So that was a side note. So now when we come to this point of view of rolling without slipping, well, for the center of mass reference frame, someone who's traveling with the center of this wheel we see rotation around the center. So as it's rotating, well, here you have r omega. So now this is the axis of rotation. Here you have r omega. Anywhere you have some velocity r omega tangent to the circle. Now, what is the velocity? Now, suppose to the ground frame, someone not moving with the wheel, that sees the wheel is moving with velocity v. Well, what should that velocity be so that this point of contact has zero velocity? Well, the velocity with respect to the ground is going to be v, the velocity of the moving reference frame, plus the velocity in the moving reference frame, which is r omega in the opposite direction. So therefore, if that point is not slipping from the point of view of the external observer, if there's no relative motion, we find the same conclusion, that v is equal to r omega. Right? The velocity of the center is equal to the radius times omega. All right, let's now put these two pictures together. So instantaneously, if you focus on very short times, one picture says that we can view this motion as rotation around the center with angular velocity omega, and then while the center is moving with a linear velocity r omega. So now in this picture, if I want to find, let's say, the instantaneous velocity of some point, let's say I consider this point on the edge of my wheel, let's say that angle is theta here. So the velocity will be the velocity with respect to the moving frame. So it's going to be, let's say, some velocity equal to r omega in this direction. And then to that, I need to add the velocity of the moving frame. Right? So I have two vectors of the same length making an angle theta, which I add together. Okay, so drawing it a bit bigger, we see that the sum of these two vectors, well, is something like this. And then this angle is theta over 2. So, and the length then we can calculate, right? If this is r omega and this is r omega, the length of this vector becomes, half of it is r omega times cosine theta over 2. So this becomes twice the adjacent side to theta over 2 in this right triangle. So that's 2r omega cosine theta over 2. So we can see it in this picture where we think of the velocities of various points as the velocity of the center of mass plus the velocity due to rotation around the center of mass. Now, if I focus in this other picture, directly think about instantaneous rotation around point of contact in the stationary reference frame. So let's say that angle is theta. Then this angle over here is going to be theta over 2, right? The reason for it is that this is the same as that. These two angles are the same. That's R, that's R. So here I have theta over 2. And then here I have 180 degrees minus theta. The angles of a triangle add up to 180. So these two things must be each theta over 2. So that already fixes the direction, right? So now if I think of instantaneous rotation around this point of contact with the ground, I'm going to be perpendicular to this line over here, to this line. And then because this angle is theta over 2 with the vertical, here I get again theta over 2. So the direction is fixed. And then what is the length? We're saying, let me draw this again. If this length from here to here is L, this picture of rotating around this instantaneous axis should give me L times omega. And to calculate L, again, I see this is R from here to here, right? This is theta over 2. So I see half of L is R times, again, cosine theta over 2. So L, again, becomes 2R cosine theta over 2. And then LR times omega, L times omega becomes, again, 2R omega cosine theta over 2. So these two pictures are consistent, and it's helpful to be able to visualize this motion rolling without slipping in both ways. Now, so if now you have this disk that's rolling, let's say we focus on one point. Maybe you put like a sticker somewhere at the edge of this disk, and then you can kind of trace where it goes, right? So it moves like this. So it comes all the way down, goes up again, etc. So that's just tracing the motion of one point on the wheel, right? You can think about that motion in various ways. So one easy way, so for example, if I pick, let's say, some xy coordinate, right? So let's say here I put this to be the x-axis, here is the y-axis. Well, to view this, what is, let's say, the coordinates of one of these points on the trajectory of one point on the edge of the disk? Well, if you just rotate around the center, right, in the moving reference frame, then your angle changes as times omega. So here, let's say theta is omega t, and therefore y coordinate becomes, for example, r. From here, let's say from here to here we have r, and then this is r cosine omega t, cosine theta, which is cosine omega t. And the x, well, in this moving coordinate, in this moving reference frame, is just r sine omega t. But then this reference frame itself is moving with constant velocity v, which is equal to r omega. So that adds r omega times t, right? That's due to the linear motion of the center of mass. So kind of if you omega t here, if you eliminate time, like you know both x and y as a function of time, and that can give you the relationship between x and y. So that's how this trajectory can be constructed. There are a few other observations about rolling without slipping. So suppose, as you go from here to here, as this point now, let me kind of indicate it with a star, get a bit bigger. Now the wheel is here, and that point has come down all the way here, right? So as this has happened, well, clearly you've rotated by an angle pi, right? And now you see, as you roll, every piece on the perimeter of this circle hits one piece on the ground. So you can think of maybe there's a rope around it and it kind of unwinds on the ground. So the length from here to here must be the length of this curve, right? That just touches the ground. And that's pi r. Therefore, this must be pi times r. And this makes sense, right? Because we know that the velocity of the center of mass is r omega. So therefore, the position of the center of mass, so let's say xcm, is just r omega times t. And now the angle that you rotate is omega times t. So if you've rotated by some angle pi, which is the case here, the point that's all the way up comes all the way down, how much you've moved is just, so this is our angle here, is r times the angle. And this ties in with this picture of kind of the perimeter of the circle unwinding, if you wish, on the flat surface where the disk is rolling. So we have multiple ways to think about rolling without slipping. Okay, so let's have a quick check question. So think for a few seconds about this. You can pause the video, and then once you've decided, come back so we go over the answer. All right. So again, we have a wheel that's rolling without slipping, and we want to see which statement is correct about the vector velocity for point P on the wheel at that instance, right? So it's rolling without slipping. The center of mass, the center of the wheel, has some velocity v, and want to see what is the velocity of point P. So again, we have two pictures, right? So one is instantaneous rotation around the center of mass. So sorry, around the point of contact with the ground, around this point. So then if I draw a line from this point, the instantaneous point of contact, or the instantaneous axis, if you wish, from here to here, then the velocity is going to be perpendicular, right? Because as it's rolling this way, it's rotating clockwise. So it's going to be perpendicular to that. So C is the only one that has the right direction. The other picture is we can imagine rotating around the center. That gives us an upward velocity, but then we have to add the velocity of the center. So we get the vectorial sum of two vectors, one going from left to right and the other going up vertically. Again, C is the correct answer. So that's the way it's discussed here, right? We have this vector going up is in the moving reference frame is the velocity, because you're rotating around the center, and then we have to add the velocity of the moving reference frame, the one moving with the center. So their sum is that. Okay, so now I want to stop and do some examples. Before doing actually examples, there's another thing I want to mention in the context of rolling without slipping. So the idea is we can write the kinetic energy of a round object that's rolling and without slipping as a sum between kind of a linear or center of mass kinetic energy plus a rotational kinetic energy. So at this point, let's take this. I think next time maybe we have time to discuss it a bit more to understand better where it's coming from. But let's take this expression. So we can write the total kinetic energy of this rolling object as a sum of the rotational kinetic energy, the kinetic energy due to the fact that in the moving reference frame, in the reference frame that's moving with the center of mass, all points are rotating around the center of mass, plus a kinetic energy associated with the motion of the center of mass. So the center of mass kinetic energy is just 1/2 the total mass of the object times the velocity of the center of mass squared. The rotational contribution to the kinetic energy is 1/2 the moment of inertia around the center of mass times omega squared. All right. So now let's do some examples. So we want to study rolling without slipping on an inclined plane. And this is similar to what you have on the homework. So you have some problems related to this. One of them, I think, is called an unfair race or something like that. So basically, the idea is we have a round object that we put on some inclined plane with, let's say, angle theta, and we let it roll down. And it rolls down without slipping. Okay. So let's say we want to find so let's say it's here, we have a height h, and we want to find the velocity of the center of mass when this object has come down, when the center of mass has come down by some vertical distance h, right? Now, if you had a block or something, if there was no rotational motion, if all the kinetic energy were translational, then we know like the change in potential energy is just mass times h times g, and that gives you the total kinetic energy, which is 1/2 mv squared, and you can easily find v from energy conservation. Now that we have rolling in addition to translation, in addition to the motion of the center of mass, the potential energy, the change in potential energy becomes the total kinetic energy, which has both the linear component and the rotational component. So the equation I can write now is mgh, that's how much potential energy I lost, must become, if you release it from rest, let's say, becomes the center of mass kinetic energy plus rotational kinetic energy. So this is what? The center of mass kinetic energy is 1/2 m velocity of the center of mass squared. The rotational kinetic energy is 1/2 ICM, the moment of inertia around the center of mass, times omega squared. Okay, but remember, if it's rolling without slipping, the velocity of the center of mass and omega are not independent, right? We just found at the beginning of this lecture that the velocity of center of mass is r, the radius of this disk or ball or whatever it is, times omega. So that means omega is VCM divided by the radius. Okay. So now plug in this expression into our equation for energy conservation. We find mgh is equal to 1/2 m VCM squared plus 1/2 ICM over r squared times VCM squared. So we can also divide this by m and multiply by 2, for example. So then we find 2gh is VCM squared, which then we factor out, times 1, plus ICM divided by mr squared. Right, so you multiply by 2, this factor of 1/2 goes away, you divide by m, we get m in the denominator, and then the coefficient of VCM squared from here is just ICM divided by mr squared. For this one, we divide by m multiplied by 2, so we get a coefficient of 1. On this side, we divide by m multiplied by 2, we get 2gh. Notice that this quantity here is dimensionless, right? The moment of inertia has dimensions mass times length squared, and you have some round object whose center of mass is at the center, then the moment of inertia is going to be some dimensionless number times its mass times its radius squared. Radius is the only length scale you have, and mass, the total mass, is the only mass scale you have. So for example, if it's a ring, ICM is just mr squared. If it's a disk, it's, I think, 1/2 mr squared. If it's a sphere, it's some different number times mr squared. So let's say, depending on how the mass is distributed, ICM is some number, let's call it gamma, mr squared. This is some dimensionless number. That depends on how the mass of this round object is distributed around its axis. So we find 2gh is VCM squared times 1 plus gamma, and VCM squared becomes 2gh over 1 plus gamma. Cm is the square root of that. So if you also rotate, you're going to get a smaller velocity at the end, because some of the kinetic energy goes into rotational kinetic energy. Another way which we can think about this problem is, instead of using energy conservation, thinking directly about forces and torques and angular acceleration and acceleration, etc. So it's a little bit of a longer way, but I think it's helpful to do it that way as well. So let's try to do it again a different way. Again, we have this angle theta. So if I think about the free body diagram of my disk, I have its weight mg acting at the center of mass. At the point of contact with the inclined plane, I have a normal force N, and then I have a force Fs, a friction force. You may wonder why we were allowed to use energy conservation if we have friction, and why do we need to have friction, right? So first, notice that there is no relative motion at the point of contact, right? So this point belonging to the disk that's touching the inclined plane instantaneously has zero velocity. There's no slipping. So the friction force doesn't act over any distance. It doesn't do work, right? There's no relative motion there. Where there is friction, they're not slipping against each other. So the friction isn't doing any work. It's static friction. And therefore, it doesn't do any work. It doesn't turn any energy into heat. So energy conservation works. Why do we need to have friction? Well, if you think about the net torque around the center of mass, you see that mg is acting at the center of mass. It doesn't apply any torque around the center of mass. This normal force N, which is here, again, it's in the radial direction, right? It's perpendicular to the inclined plane. So it's pointing toward the center of this circle. Again, it goes through the center and doesn't exert any torque. But if the angular velocity is changing, which it has to because it's tied to the velocity when the object rolls without slipping, we have the velocity of the center of mass is just r times omega. So if VCM is changing, omega has to be changing, there has to be an angular acceleration. It means there has to be a torque around the center of mass. And only friction can supply that torque. So we need to have friction in order to have rolling without slipping. All right, so these are the only three forces. So we can pick maybe a directional parallel to the inclined plane to write our equations of motion. There is no motion for the center of mass perpendicular to the inclined plane. So if I think about my force as well, N is perpendicular to this direction, so it doesn't give me a force in that direction. mg has a component that's equal to mg sine theta in this direction, and then I have to subtract fs. So that's the net force in this direction parallel to the inclined plane, and that's mg time, that's m, the mass times the acceleration of the center of mass. The torque equation, what does it read? Well, we just said that n and mg don't have any torque around the center of mass. Fs gives us clockwise torque around the center of mass, and the torque is Fs times r, right? The distance is r from here, where the friction force is applied to the axis that goes through the center of mass, and that must be the moment of inertia times alpha, the angular acceleration, which is also equal to ICM, the acceleration of the center of mass divided by r. This follows from just taking the derivative of that equation, right? R doesn't depend on time. If I take a time derivative here, the rate of change of v, which is a, is r times the rate of change of omega, which is alpha. Okay. Now we just maybe divide this by r again, so we find Fs is ICM over r squared times ACM. And if I insert this expression for the friction force in my force equation, I find mg sine theta is m times ACM plus, I take this Fs to the other side, ICM over r squared ACM. If I divide this equation by m, I find g sine theta is ACM times 1 plus ICM over mr squared, which we call gamma. So I find the acceleration along the inclined plane to be g sine theta over 1 plus gamma, right? Remember the equation we found for VCM squared? So we found VCM squared to be 2gh, 1 2gh over 1 plus gamma that we found from energy conservation. So if this is h, this is L, the distance you move along the inclined plane, h is actually L sine theta. So this is 2gL sine theta over 1 plus gamma, which is equal to 2 ACM that we found times L. And these are consistent, right? We had this equation from kinematics that final velocity squared minus initial velocity squared is just 2 times the acceleration times the distance traveled. And we see the two ways give us the same result. So I could, from this acceleration, just use this expression, Vi is 0, to find the final velocity squared of the center of mass, and I would get the same thing I got from energy conservation. All right, I think that's a good place to stop.